Welcome everybody to the next session of the day. After we had in the morning the session of more fundamental processes of nanoparticles, we're getting now slightly bigger with our session of process and box models of aerosol chemistry and physics. This session will be split in two parts. In this first part, we will be hearing more about physical and chemical processes relevant for cloud formation and aqueous phase chemistry. And our first speaker this afternoon will be Dr. Mary Barth. She's a senior scientist in the atmospheric chemistry observations and modeling laboratory and the mesoscale and microscale meteorology laboratory at NCAR. So please welcome Mary to the stage.
Great. Good afternoon. And thank you for giving me the opportunity to talk about the understanding of organic acid formation in cloud chemistry using box model calculations. I really want to acknowledge my co-authors, especially Chris Lawrence, who's a graduate student of Sarah Lance at the University of Albany. I'm going to begin this presentation by defining what cloud chemistry is. It's aqueous phase chemistry, but it's not only aqueous phase chemistry. It also includes changes to the gas phase chemistry due to that separation of reactants. And you can see that in the bottom in the black, a really good example of separation of species. The HO2 plus NO reaction will change its reaction rate because HO2 drifts off into the liquid phase when it's in the cloudy environment. In addition, I think cloud chemistry should also include changes to the photochemistry due to scattering by the cloud particles. So shown here is a schematic doing really simple depiction of organic acid formation. So really the ingredients are having aldehyde and OH. They dissolve into the cloud droplets and will oxidize. The hydrated aldehyde oxidizes to carboxylic acid. And then that can actually go on and oxidize further to form dicarboxylic acids or different carboxylic acid. So that's really simple. A more complicated version is, once did I hit that? There, a more complicated version is shown in the schematic that Barbara Irvins published several years ago. And this is really just showing the formation of 6 organic acids, formic acid, acetic acid, glycolic acid, glycolic acid, pyruvic acid, and oxalic acid. And it's oxalic acid that is our dicarboxylic acid that will contribute to secondary organic aerosols. So a few years ago, I led a model in a comparison of 5 cloud chemistry box models to assess what the state of knowledge of organic aqueous phase chemistry is, because I'm keen on trying to get this into our 3-dimensional regional and global chemistry transport models in a faithful way. And so we conducted this model in comparison with the simulations at a fixed point that were based on measurements taken at Whiteface Mountain in upstate New York. And you can see where that is located in the upper left. These were 20-hour, the cloud that was there for 20 hours. And so we did our simulations for this 20-hour period. The conditions were for the 16th of September, 2016. Because that is actually when we were all up there and found, hey, this is a really good cloud event. What we learned from that study is that there were a lot of model differences that arose from us using different chemical data, in particular the Henry's law and the dissociation constants, as well as reaction rates in the aqueous phase chemistry. And then to some extent, because we had different chemistry represented in our aqueous phase chemistry, as well as the gas phase chemistry. So consequently, the hydroxyl radical and the HO2 radical differed, and that caused different formation rates in organic acids. And so I just wanted to emphasize or show you how that variability played out. So shown here are 6 panels that are time series for the 6 different organic acids I mentioned earlier. And each line in each panel is a different model that was run. And you can see that these are all log plots and that there is order of magnitude differences in the number of these organic acid predictions, anywhere from formic acid in the upper left to oxalic acid in the lower right. A couple of things to point out, though, is that we all seem to show that formic acid is that these organic acids are all being produced, especially in the first 3 hours of our simulations. This is especially true for formic acid and for oxalic acid. And also, when we got to the second day, when the daylight came back, at some point during that daytime, the organic acids often reached a maximum value in concentration and then started depleting. And that indicates that source and sink and dependence on the OH aqueous phase concentration. Okay, so that's what we learned in very much of a nutshell. There's a lot more detail in the paper that I cite there. But here I am repeating the slide, and I emphasize that we did these simulations at a fixed point with a 28-hour cloud encounter. And I'm going to say why, how representative was that model configuration. I thought that this in a comparison was really useful, but I didn't really think it was that realistic because what air parcel stays at a location for 28 hours? And you could think about it, well, maybe it's the same air coming in, or same representative air coming into that location, but I still don't feel comfortable about that. And in fact, past studies, like the one that I show here on the bottom by Graham Feingold and others, have run detailed modeling, or in their case, a large eddy simulation model, where they launched at least 500 trajectories and then recorded how often each air parcel was in contact with the cloudy environment. And typically that was 15 minutes, ranging up to about 45, 50 minutes. So much shorter than a 28-hour time period. And I've done some similar calculations in the past, more with cumulus clouds, convective clouds, and also same sort of answer, 15 minutes to an hour. So I decided that, hey, next time that we do something like this, we're going to be more realistic and make use of trajectories to conduct these calculations. And that next time happened when Sarah was willing to have me work with her student, Chris. And he's interested in understanding the organic acids formations during the polluted event that happened at Whiteface Mountain in New York. So this polluted event was associated with a heat wave. These are showing WRF-Chem simulations of the sort of 2-meter temperature overlaid with observational data. So that should assure you that our model simulation is fairly good. And what you see is that on the left is the surface or 2-meter temperature from a few days before the polluted event. It was hot in the Midwest and it moved to the New England region, where you can see on the right that the high temperatures persisted over to the east. This affected the particulate matter. Hopefully I didn't do that twice. This affected particulate matter as well as ozone. Here's an example of the particulate matter where a few days before the polluted event, skies were clean. And then as this heat wave went into New England, the PM 2.5 reached values of, 20 micrograms per cubic meter. At Whiteface Mountain, they've been taking cloud water measurements for decades. They measure inorganic anions and cations. That was began with the acid rain studies. And then more recently, they've been measuring total organic carbon and water-soluble organic carbon, as well as even more recently, these organic acid anions, and they use a PILS instrument to help get that measurement. Okay, and so what they found in 2018 are that typically the most common organic acids were formic acid, acetic acid, and oxalic acid. You can see in this chart on the right that not only those organic acids, but as well as sulfate, ammonium, and nitrates. Typically, they would find that these organic acids were 10 microequivalents per liter. or less in concentration. But during this 1st and 2nd of July 2018 polluted event, which are shown in the circle markers, that the organic acids were 8 times greater than what was typically found. So quite a bit different. Okay, so this is what we did to try to address the modeling part of how did those organic acids become so high. So we started with Chris running high split back trajectories. He did 3-day back trajectories ensembles to find a potential source location. About 2 days beforehand, that air was in central Missouri, near the surface, and so that's where we said the air was coming from. We then took that information and ran WRF-Chem for a 5-day simulation, starting 5 days before the event and going through the event. So it was shown, and then we launched forward trajectories from central Missouri. And so these are examples of 4 times launch times that we did. And they're all starting in central Missouri, and they're going for the remainder of the simulation. And you can see how that air is going from central Missouri up towards the northeast and up into upstate New York. On the left are altitude. It's colored by altitude, showing that most of these trajectories stayed within a couple of kilometers of the surface. And on the right shows the NOx concentrations of the trajectories, showing that some of these trajectories went over Chicago, getting NOx emissions from Chicago. So kind of an interesting combination of biogenic and then possibly anthropogenic VOCs and NOx entering the system. Okay, so once we had the information from WRF-Chem along those trajectories, we wanted to use more detailed cloud modeling, more detailed gas phase modeling to look at what happened along those trajectories. And so we used those WRF-Chem trajectories to initialize the concentrations, prescribe the environmental conditions, the emissions, and the background air for mixing. And then we ran the BoxMox gas phase box model with 2 chemical mechanisms, MCM and the Mozart T1 gas chemistry mechanisms. And we went to look to see how that affected the organic acids and if there were any substantial differences between those 2 mechanisms. And so here are some results for formic acid. You can see indeed a lot of formic acid was produced in that first day. And then it tapered off to lower values to around 100 parts per trillion. The region between the red dotted vertical lines is when the trajectories were near Whiteface Mountain. So by the time they got to Whiteface Mountain, they were only on the order of about 100 parts per trillion. And that was really much less than what was needed to match the formate concentrations that were measured in the cloud water. So this is showing that gas phase chemistry is not sufficient for the to explain the measurements. That was true for acetic acid as well. You can see here that MCM and T1 has some differences between how acetic acid is formed, but nevertheless, they both underpredict how much acetate was measured. And so if it's not gas phase chemistry, we might be missing some gas phase chemistry, but if it's not gas phase chemistry, could cloud chemistry explain those high organic acid concentrations? And so we went back to my cloud chemistry box model. We used the results from the Mozart T1 BoxMox to initialize the concentrations and then Whiteface Mountain measurements of liquid water content and state variables to run just 3-hour simulations of cloud chemistry. And this is what we learned from these simulations with a cloud chemistry model. On the right is the aqueous phase concentrations of formic acid and acetic acid. The dotted lines are the measurements and the solid lines are the modeled concentrations. And again, it's vastly underpredicted. And in fact, you see formic acid being depleted rather than being produced, and acetic acid not really changing its concentration due to the cloud chemistry. The left panel shows the total, the gas plus aqueous phase concentration, and I think that depletion of formic acid is even more emphasized. So one of the things I thought was curious is that in our September simulation, we saw in general formic acid and these organic acids increasing over this long time period. But in this other case in July, we see this decrease, especially in formic acid. And I was trying to figure out, well, how can I try to quantify this and come up with a way to explain these differences? And so my thought was, hey, maybe we should put this in some sort of parameter space. VOC NOx parameter space did not quite make sense. In fact, the NOx concentrations were quite similar among all these model simulations. So I put it into this initial organic acid, that's all the organic acids summed together, and initial aldehydes, all some aldehydes summed together, that parameter space. And so what we find is that the aqueous phase formic acid, which is being shown here, that's changed is lower when you have initial aldehyde mixing ratios and a lower initial organic acid mixing ratios. Also I found from doing a bunch of sensitivity simulations that the production versus the destruction depended on that chemical data, because I did try other data for the Henry's law and dissociation constants. It depended on the temperature and likely other environmental variables that I'm not showing here. Curiously, there are a couple of places where you see destruction happening for the same acids and aldehydes as you see some production, and like, hey, what's going on there? And then so part of that, I looked at a couple of these particular cases specifically, and saw big differences in the aqueous phase concentration of OH, differences in liquid water content. And so there's like not a clear one thing that's making these answers different. And then I thought about what I said at the beginning, that cloud chemistry includes aqueous phase chemistry and gas phase chemistry changes. And so looking at the change in the total formic acid is shown here. And now we see clearly that all these the simulations for the July case are showing formic acid destruction, and that yet we still see production of formic acid in the September case. And the main difference between those is that initial total acids for the September case compared to the July case. So that's as far as I've gotten. I've just have been thinking about this over the last couple of weeks. And so I really would welcome any comments and ideas about how to understand organic acid formation. So just I want to end here with my key points. I think it's really important to remember that there's meteorology going on affecting the clouds and chemistry, that the production of organic acids is sensitive to the chemical data that we're using in our models. Our gas phase chemistry mechanisms are not able to explain the measurements at Whiteface Mountain. And so we're going to push forward and trying to identify other important organic aqueous phase reactions that may be needed to properly represent organic acid formation in 3D models. And with that, I would be happy to take questions, and thank you.
Thank you, Mary, for this excellent talk. Do we have questions? Yeah, Kostas.
Great talk, Mary. So I wonder if formic acid and in general, those small carboxylic acids are, as you already know, super complex, right? So correct me if I'm wrong, but I think that microbial activity in the droplets can also affect them. So do you have a comment on that?
Oh, microbial activity. I'm not the best expert on that, but my thought, little I know, is that it's mostly affecting the peroxides, which can then affect the radical species and then subsequent aqueous chemistry. There might be other experts in the room that can also talk to that. They can. So yeah, so Faye is saying that you see stuff in the collected water, but not in the actual cloud droplets.
Any other questions?
So, with regard to points 2 and 3, I'm curious how sensitive you are to emissions, right? So assumptions and emissions. Right, the distribution of emitted compounds will influence their reaction rates and how much, different products that partition they make. And then also the way those compounds are lumped in a model like WRF-Chem influences the Henry's law and things like that. So I'm just curious later around
Right,
the
'cause-
sensitivity to those.
Right, yeah, so definitely the WRF-Chem simulations are affected by emissions, and the gas phase only simulations are affected by emissions, because we did include that as air parcels got into the boundary layer. In those cloud chemistry box model simulations afterwards, there were no emissions. So everything will depend on those initial concentrations that were previously affected by the emissions, right? Doing sensitivity tests directly with the emissions, I haven't done, and I don't think I've seen other people do. So that's an interesting idea. Thank you.
And let's move on to our next speaker, which is a virtual presentation.
Okay, so first of all, I want to thank the organization committee who invited me to present this talk about water activity, such extension of aerosol nanoparticles. So I first start with a simple Kepler equation, which we use it to describe hygroscopic properties of aerosol particles. This Kepler equation shows that if you know water activity and Kelvin term, you can completely describe hygroscopicity of aerosol particles. In this case, when the particles are quite big, for example, bigger than 100 nanometers, you can forget about Kelvin term and use only water activity term, and use it to explain all hygroscopic properties of aerosol particles. It's sometimes enough to use aerosol organic model Wechsler-Leclerc and Zuent model IAMFAX or Peter and Krandenweit model. But situation become more complicated when particles become smaller than 100 nanometers due to high surface area to volume ratio. Both bulk and surface properties of nanoparticles need to be considered. To take into account interaction between surface and volume, Pythonic models have been developed. There are some models the last a few years ago was developed. Royal, Adewite, Priesel, and recently Schmedding and Zuent models. But this is one problem because it's difficult to verify the proposed model. There are no methods for measuring the activity in surface tension of nanoparticles smaller than 1 micrometers and even less than smaller than 1 micron. But a few years ago, Chang and co-authors suggested a new approach to calculate thermodynamic properties of aerosol particles below than 100 nanometers, where the Kelvin term become very important. They suggested this very simple logarithmic form of Kepler model. And they show if you have a hygroscopic growth measurements, a different relation humidity for different aerosol diameter initial, you can plot this figure and use a logarithmic form of Kepler equation as to fit this dependence and obtain surface tension and water activity as a fit parameter of the Kepler equation. This is very original approach was suggested by Chang et al. It's allowed to retrieve surface tension and water activity independent for nanoparticles. So, first of all, as you see here, it's experimental methods, and after that, the theoretical. As experiment method, it must be very careful to determine all parameters of the model, because you need to know hygroscopic growth factor with very high precision. So what we need to do first is to know the real dry mobility diameter of aerosol particles. Initial particles have a regular shape, and we need to use special restructuring mode to convert this particle into mass equivalent diameter. So this is first stage of the measurements. It's very important. The next stage, each hygroscopic growth measurements, which calculated as a between mobility diameter at given relative humidity to initial. So when we use the differential Köchler analysis model, we reproduce water activity and surface tension, and after that we compile our data with a model. For water activity, we use a single solid model, ammonium sulfate, aerosol inorganic model, and for glucose, we use aerosol ion fax model by Zuent. For mixed particle, we use also ion fax, and for solute activity, we also mixed particle. We have we compile with ideal model. For surface tension, we use some parameterization. One of them is Dacher et al. Parameterization, another Propacher and Klett parameterization, and Aumann et al. Parameterization. So for mixed particles, also very useful model Li and Liu, which was developed for single particles and for mixed particles. For mixed particles, we have two equations. One of them take into account their non-interaction effect, but another take into account real interaction effect between solid-solid and competition absorption at the surface. So this is first Xiaotian results, which was obtained by using Xiaotian system, and we see some ammonium sulfate, glucose, their mixture 4:1 ratio, and their mixture with 1:1 ratio. As we can see that at high relative humidity, we have at the same growth factor, we have different equilibrium value of saturation ratio. It's okay because in fact, for the same growth factor, equilibrium value must be high for small particles. So, and now I'll show some results with differential Köchler derived parameter for ammonium sulfate first, and using this approach. And we can see water activity and surface tension, which was obtained based on this ammonium sulfate measurements. So we can see that water activity are in good agreement with another model like aerosol inorganic model, Chang and model, and Clegg model, and a lot of them are very good agreement with our data. And surface tension model also very good agreement with Dacher model and Propacher and Klett model, but up to 0.5 mass fraction. Above this, due to particle solidification, we have a strong deviation between empirical model by Dutcher and Perpacher and our experimental results. The next example have the same for poor glucose particles. We see Descartes-derived water activity for nanoparticles. It's very good agreement with bulk measurements. It also very good agreement with surface tension model with empirical Raman measurements with bulk obtained with bulk method. This is very good agreement. So another point, this is Lee and Lu model. This is Lee and Lu model. It's a little bit difficult because it's a function of solid activity. We need first to transform water activity to surface activity. We did it, and after that we can plot the surface tension of a surface ammonium sulfate activity and as a function of glucose activity. And we have a good agreement with this model, and we see that excessive absorption on the surface have a negative value. This indicates that both ammonium sulfate and glucose are the surface inactive compound, because when we increase concentration, surface tension on the surface of the droplets increase dramatically. And now some properties of mixed ammonium sulfate, glucose and glucose particles with different mass ratio, 4:1 and 1:1. And we see that at the small mass fraction, we have a good agreement with the models, but above 0.3 model, we have a strong deviation between ion Fox model and separate solid volume additivity models. And the very interesting result, when we have a mixture, surface tension of, for me, a little bit different from the ideal model. Especially, we can see that for ammonium sulfate glucose with 1:1 ratio, we see that initial surface inactive compound at high mass fraction becomes surface active. It means that we have specific interaction between inorganic ions and organic molecule, which leads to formation of non-polar quasi-macromolecule of glucose, which are not polar and tends to place on the surface to decrease surface energy, gives energy of the molecule, of the droplet particles. So in principle, the main conclusion of this experiment and using DECA model, we can set the following. The DECA method can determine water activity in surface tension of a resolved particle much smaller than 100 nanometers of basis of Asian dendrimer data. The wide particle size range allows for determining the water activity and surface tension of highly supersaturated aqueous solution under conditions that are not acceptable to another method. The high concentration range allows observing a non-monotone change in the surface tension followed by a combination of Selton out effect followed by the particle solidification. In principle, additional material can be found in this paper. Thank you very much for attention.
Hi, this is Ryan Schmedding from McGill University. I was wondering, so you looked at glucose, which mixes fairly ideally with water, but have you considered looking at particles that might undergo phase separation as well with this technique, or is that possible?
Yes, we can see phase separation for mixed particles. Yes, we have a strong deviation we see a different pattern for water uptake before and after phase separation. And we can see that.
Evgeny, you were talking about at very high mass fractions of solute that there might be problems with solidification of particles. Could you expand a little bit more on that? Do you think that solidification happened and where that would be the case?
Yes, solidification is very important because when, as I said before, for example, like this one, we see that hygroscopic growth, the same hygroscopic growth, small particles have a higher relative humidity equilibrium. But this is not for the for glucose, for example, and mixing glucose with ammonium sulfate because they are in the amorphous state before the phase transition. And we can see the pattern, different pattern of water uptake before 84 relative humidity and after that. This is infection point, means that we have really here moisture-induced phase transition when the particle, semi-solid particle transform into solution droplet. And this is phase state, of course, limit, it's a low limit of concentration which we can use. Because due to this limitation, we have a very high very high mistakes like this one. This is due to solidification. This is amorphous state of the system.
Thank you very much. Let's thank our speaker again. Next up, we hear a presentation by Xiaotian Chu. He's a PhD student at the University of Illinois in Urbana-Champaign.
So good afternoon, everyone. Thanks for providing this good opportunity. I'm Xiaotian from University of Illinois. I'm going to share with my recent work with everyone. So my topic is about quantifying the impact of surfactants on cloud condensation nuclear activity with a particle result model. So let's start with what are surfactants. So by definition, surfactants are just chemicals that could reduce the surface tension of the medium very dissolved. So it stays at the surface of particle and depends on the amount of the surfactants. It can either fully cover as the organic fumes or just partially cover the inorganic core. And because it can reduce surface tension, so it can impact the seasoning activity of the aerosols. But for a long period of time, so we use the Kappa-Kohler theory to describe the well-mixed inorganic, organic mixtures. But if we focus on the equation, we can see there's a parameter, sigma, which is which we are still using the surface tension of constant water, which is not correct. So there's a recent work that considering the surfactants as a film on the aerosol particles, and it re-evaluated the color curve, and we can see that there's a dramatic decrease for the critical supersaturation. So since a lot of people talk about PyPartMC today, I will save you guys some time. So our group will use the PyPartMC. We consider each part is a particle result model, so that we can consider each particles. But just as we mentioned the research, we also want our particles consider the surfactants, then the particles can look like this, which leads to our goal of this research. So we want to find a method that we can implement it into our PyPartMC mosaic so that we could consider the existence of surfactants and quantify the impact of surfactants on the seasoning activities. So since surfactants can impact the surface tension, now as we are making assumption that each particle is having the fumes, and you can see that each particle have different composition and each of them has different surface tension. Now for the couple color theory, how should we represent the surface tension here? So we took a method called effective surface tension. It's a surface average based method that includes several parameters. I will show you guys one by one. So it first assume a liquid phase separation of a core shell morphology of particles that consider the inorganic core and the organic shell. And second one is the minimum shell thickness, which is based on the single molecular diameter. And by comparing the shell volume and the organic volume, we can calculate the surface coverage. That's how this method calculates the effective surface tension. So by recalling the previous color curve and surface tension, we know that the surface tension actually changed during the particles growing process. So we want to find the effective surface tension at a critical supersaturation point. So previously, when we just consider constant surface tension, so simply speaking, we just need to find the derivative equals to the 0 of the color theory. And because of the denominator part and the exponential part is always positive, so we only need to consider this f here. And based on the f, we apply the partial f. And after several times iteration, we can calculate the critical diameter and then the critical supersaturation. So now this surface tension is a function of diameter, and we can still follow the previous method, but the only difference is everything becomes so complicated. So we need to reevaluate everything to recalculate the critical diameter and critical supersaturation. Okay, so that's basic the methodology part. After the implementation and reevaluation, let's see some results. So here we took an example case of a single particle of 0.15 micron dry diameter dry particle with chemical composition shown in the pie chart. So on the right hand side, you can see that actually for this condition, the critical supersaturation decreased by 45%. And also at critical supersaturation point, the surface tension here is actually just 54 rather than 72, which is the value for water. And we also run 24-hour urban plume scenario case with PyPartMC mosaic. And so this figure shows the comparison of the critical supersaturation with the dry diameter for each particles. And the CST is just a previous color theory with consideration of constant surface tension. And this one is the relative error of these two methods. So, and we also consider the activation ratio for this whole population. So for example, if we pick 0.3% as an example, which is like common environment saturation ratio, and you can see that if we use the effective surface tension, and the activation ratio is 0.72, while it's only 0.6 for the previous color theory. So far, we are talking about the impact for single particle level or just one population level, but we do want to expand our research to a larger scale. So our group developed coupled the PyPartMC into the WRF so that we can just like enable WRF 3D particle resolve capability. So this is but like it's pretty expensive, so we don't want to run simulation again. We just took the previous results and reevaluated with the new effective surface tension methods. And you can see that the average relative error of over the whole simulation domain is like around 24%. But for some cases, the relative error can reach as high as 85%. And because the PyPartMC's capability, So each gray box contains lots of particles. So here we also pick 3 distinctive places. So one is Davis, where we are having a meeting now, and we can show what particles looks like, and also the comparison of the activation ratio. And their second location is the ocean, and third one is the mountain. So so our goal is to study the impact of surfactants on the cysteine activity, which will ultimately lead to the impact on the cloud formation process. But it's improbable to consider cloud formation at the near surface level. So here we also construct the vertical cross sections so that we can see the impact at a higher level. And because the cross section just start from the ocean, you can see like for both 3 panels here, the bottom corner is pretty low relative error, and similar like the mountains. But on the other hand, we can see places like the Bay Area and the Reno, which is the urban cities area, they usually have the larger relative error. And one thing we need to notice is that this highest relative error occur at the surface could persist up to 2 kilometers or even 3 kilometers. So this could potentially impact the formation of some shallow clouds or even some middle clouds. And at last, in order to take advantage of the particle result capability, so we also apply the possibility density function to the relative error on all diameters. But interesting is you can see that actually the largest frequencies occur at the 10%. So we think it probably because there's large simulation placed over the ocean, which has a lower relative error on CCN. But consider that the particle with diameters that larger than 100 nanometers or lower than 10 nanometers usually just have the negligible impact on CCN activation. So we narrow down our size diameters, our size into 3 different intervals. So by it's very clearly to show that the largest relative error occurs at 40 to 70 nanometers. So we can just go through the summary quickly. So we want to study the impact of surfactants on CCN. Here we find the method, we implement it into our model, and we quantify the impact of the surfactants on CCN from single particle scale to one population level, and last to the regional scale level. And for our next work, for our next step work, and we want to apply the OC ratio to replace our current liquid phase separation assumption to find the compromise between the Kappa-Color theory and effective surface tension. But in order to do that, we need to first refine our SOA scheme, because currently the sorghum in our model only capture the first generation of the oxidized products. So that we want to refine the scheme to capture more species with higher OC ratios. So that's pretty much my talk today. So I'm happy to take any questions.
Thanks for that talk. A little bit tangential, but could you provide examples for what might be typical surfactants in the real atmosphere, and how these surfactants might oxidize and therefore lose their ability to serve as surfactants?
I would say that's pretty chemistry problem, but so I would say that's a little bit too chemistry problem. I'm not sure I can understand correctly, but so there are many organics in the atmosphere, and I think you can just consider some organics can just stay in the core phase, but some can go to the surface of aerosol particles. So those particles, aerosol particles those parts of organics can be called as surfactants. But here we use the assumption of the liquid phase separation. Actually, this assumption didn't consider property of the organics. So we just assume all the organics are in the surface of the aerosol particles.
I have a bit of a kind of related question as well. Do you consider, when you partition these things to the surface, do you consider any sort of feedbacks on the internal composition of the particle, like things being depleted out of the interior as they move to the surface?
I'm sorry, can you?
Do you consider like feedbacks on the internal composition of the particle once you account for surface partitioning? Like, do things get depleted out of the interior of your particle, and does that affect the CCN activation in your model?
Didn't do that, but I think we can do that because this is our model is a particle result model. So actually we can analyze we can pick any single particles and we can analyze which, just like the example case, I would say. Like the example case, you can just know the chemical compositions and analyze the things you want, I guess. Yeah.
Cool. Thank you.
Any more questions? Ken?
What's the computational cost of the model?
Computational cost.
Yeah, the full model.
It's actually just a box model, so it runs pretty fast. So for example, here we run the 24 hours model, 24-hour urban plume scenario case. It usually just costs like 2 or 3 hours, yeah, to run 24 hours. But I would say it's pretty expensive to run the PyPartMC, but I didn't run that, so some of my group may run that. I just use the results. Yeah, this one is expensive.
And the first speaker in the session is Shantanu Yata. He's an associate professor at Colorado State University, and his research interests lie at the intersection of energy and the environment, and he leads the laboratory for air quality research.
Okay. Thanks, Nicole and Thomas, for letting me come here and present some of our work. So I should say that this work was primarily performed by Charles He and Kelsey Bilsback, who were group members, but now have moved on and doing great things in the world. This work was sponsored by the DOE ASR program, NOAA, and US EPA. So this figure is a little dated from Jimenez 2009, but it's a compilation of aerosol composition data from aerosol mass spectrometers from regions around the world, and makes this point that about half of the submicron atmospheric aerosol mass is made up of organic compounds, or as we lovingly call it, organic aerosol. The remainder is a simple mixture of a few different inorganic species: ammonium sulfate, ammonium nitrate, and if you live close by the sea, sodium chloride. And many such studies have been performed over the past, since 2009. Here is a figure from a more recent study, which is a meta-analysis of aerosol mass spectrometer data in Western Europe. And the picture really hasn't changed, that about half is inorganic, half is organic. But some further insights have suggested that this organic portion is dominated by secondary organic aerosol, or that formed from the oxidation of volatile organic compounds. Now, aerosol formation is quite complex, and I'll describe some of the processes by which it arises. So you can have sources like wildfires, refineries, motor vehicles, and the biosphere that can release emissions of both reduced hydrocarbons, but also oxidized VOCs. They can react in the atmosphere by interacting with oxidants, OH, ozone, nitrate, radical, and form the oxidized products. These will continue to react with oxidants through a process of multi-generational aging, where the properties of these oxidized products will continue to change. Some of these will partition into the particle phase, and condense on pre-existing aerosol, or as we've learned today, nuclei to form new particles. Some of these oxidized species, if they're water soluble, will be taken up into the water fraction of an aerosol and then be processed within that aqueous solution. But they can also be taken up into clouds and participate in chemical reactions to form additional products. If we now take one of these perhaps dry organic aerosol particles, you can have oxidants colliding onto the surface of the particle, and you have heterogeneous chemistry that will again result in reactions. The species within the particle phase can interact with sunlight, photolyze, perhaps fragment and evaporate. But you can also have species within the particle coming together to form oligomers. And here I'm probably characterizing only a fraction of all of the SOA processes that we are fond of. And so the point here is that these processes need kinetic process level models because the speeds at which these processes happen in the atmosphere can vary quite significantly depending on where you are and when. Oh, and I forgot about deposition. So in the past a few years, Jeff Pierce's group and my group at CSU have put together this kinetic process level model that we call SOM-TOMAS. It's composed of two things, SOM, a statistical oxidation model, and TOMAS, that stands for two-moment aerosol sectional model. SOM simulates the oxidation chemistry of the VOCs and the oxidation products in a carbon-oxygen grid, tracking both functionalization and fragmentation reactions. And then TOMAS takes care of the microphysics, coagulation, nucleation, condensation, evaporation. The feature about SOM-TOMAS is that it's a tunable model. So we can develop parameters up to 11 parameters that can simulate a wide range of processes: gas-phase chemistry, heterogeneous chemistry, auto-oxidation reactions, phase state influence, gas particle partitioning, and oligomerization reactions. Okay, so we've used this kinetic process level model in several studies over the past few years, and I'm going to show you some of the results from 3 different case studies. One where we apply this model to look at the phase state of SOA, another one where we bridge chamber and OFR or flow tube data, and then the third to study wall artifacts and environmental chamber experiments. Okay, so this first study was done by Charles He to try and look at the evolution of the particle size distribution and extract information from that data to constrain the particle phase state. So there's previous studies that have suggested that the SOA that you can generate from photo-oxidation of alpha-pinene produces SOA that's semi-solid or viscous. And so I list some of these studies here. What you'll note is that I've in the red box shown the bulk diffusion coefficient that I was either measured directly or estimated. And so there's sort of 2 things to note here. One is that the range of that bulk diffusion coefficient, or dP, is within the sort of semi-solid viscous range. And this is again for SOA that was produced under dry conditions. And then the second is that there's a fair amount of heterogeneity across studies, right? So there's a lot of uncertainty in what the actual bulk diffusion coefficient is. So we took, in this particular work, we took SOM-TOMAS and we updated it to now account for the phase state of the particle and how it influences gas particle partitioning. And so for that, we relied on some equations and schemes that Rahul Zaveri had presented in an ACP paper in 2014, which simulates the limitations to either condensation or evaporation based on the phase state of the particle. And while we were at it, we also considered a scheme where we model the formation and dissociation of dimers, and that's because dimers have been attributed to the increase in viscosity of a particle or a reduction in the bulk diffusion coefficient. Okay, so what we do is we take some sample chamber data. This comes from Caltech, thanks to John Seinfeld, and we run the model and fit the model to develop parameters such that it can explain the observations of SOA mass concentrations shown on the left and the O2C data shown on the right. And we do that by prescribing the diffusion coefficient. So the mass and the O2C data don't have information inherent within them to constrain the phase state or the bulk diffusion coefficient. But now if you run the model in a forward way, and look at the model measurement comparison of the particle size distribution at about 3 hours, where the SOA has leveled off, you see that it produces a range of results. The model produces a range of results for different dB values. And it seems like a dB value of about 3.4 times 10 to the negative 15, which is squarely in the semi-solid viscous range, seems to reproduce the particle size distribution the best.
Having constrained the particle phase state, we ask the question, can we now use that information to constrain the oligomerization process? So here, I'm again showing comparisons of the model predictions for SOA mass on the left, of SOA O to C on the top right. And what you can see is that if we allow the model to compute the bulk diffusion coefficient based on the composition of the secondary organic aerosol, which is done by first determining the glass transition temperature and then through a set of equations determining the dB, we can actually predict the change in the dB as a function of time as the composition is dynamically changing in the particle phase. Okay, moving on to the next study. So this is Charles's last paper as a PhD student, where he took the model and tried to resolve differences in SOA production between environmental chambers and flow tubes. So as we all know, chambers and flow tubes are workhorses that we use in the laboratory to understand SOA systems. And I apologize if your favorite chamber isn't in here. Okay, so SOA data from both chamber and OFR experiments do not necessarily agree with each other. So on the left, you can see some data from Andy Lamb's analysis, where the SOA mass yields between those derived in a chamber versus a flow tube are slightly different as a function of photochemical age. You can sort of see the same result from a study from the PSI group. And it's obvious for there to be some differences because the oxidant concentrations can vary by orders of magnitude. The time available for partitioning for the condensable vapors is quite different. And given the varying surface area to volume ratios of the chambers and OFRs, the walls may interact in unusual ways. Okay, so what do? So we first take some chamber data for alpha-pinene photooxidation, and we use the SOM-Thomas model to develop parameters that can reproduce both the SOA mass concentration and the O2C data in a chamber. Okay, we then take those same parameters and try and predict the SOA mass yields in a flow tube as a function of photochemical age. So what you see here are some model predictions compared against measurements shown in black. So if you look at model A, where we assume a liquid particle and only gas phase chemistry, we overestimate the SOA mass yield by several factors. If we now include the influence of particle wall losses, size-dependent particle wall losses, we'll reduce the mass yield a little bit. We now include the influence of vapor wall losses inside the flow tube. Our predictions get even lower. We include now a semi-solid particle phase state that's further lowered. Oligomerization increases the mass yield a little bit, but not by much. But really, it's the models F and G that you can see in the top right there that can reproduce both the mass yield trends with photochemical age and the O2C trends. The difference between F and G is that in F, we assume that the nucleation happens immediately after the alpha-pinene is introduced at the front end of the OFR or the flow tube. In model G, we assume that nucleation happens throughout the flow tube. What we see is when we compare the model predictions against the measurements of the particle size distribution, neither of those seem to get the particle size distribution right. So the model F is shifted to the right, and then model G is shifted to the left. So we then say, okay, what kind of scheme can help us reproduce the nucleation within the flow tube that might help get us in better agreement with the measured particle size distributions? So we sort of employ the equation 1, which is completely made up, right? It's a Gaussian distribution for the nucleation, has no physical basis, right? But as I'll show you on the next slide, it sort of does great. And then equation 2 is where we're using insight from some of the cloud experiments where perhaps the nucleation or the new particle formation rates are informed by the production of extremely low volatility organic compounds. So these could be auto-oxidation products or perhaps even gas phase dimers, as the Helsinki group has shown. Okay, so now if we employ these different nucleation schemes inside the flow tube, our mass yield and our O2C comparisons don't really change, but we start to see some improvements in our size distribution. And it seems like a nucleation scheme that is linked to the production of low volatility organic compounds or extremely low volatility organic compounds can help us bridge that gap. Again, making the point that there's information embedded within the particle size distribution that can be harnessed to try and constrain both processes and properties. Okay, final study. So this was done by Kelsey Biltzbach, where we looked at chamber artifacts or wall artifacts. Okay, so we've all known that the way to produce SOA is to take a VOC and hit it with an oxidant. You form some condensable vapors, which will then condense onto some pre-existing aerosol. But the problem is the walls will start to interact with this fundamental process. Some of the particles will get lost to the walls. Some of the vapors or the condensable vapors will get absorbed into the particle, into the walls of the chamber. But some of the vapors could also be lost to the particles on the wall, right? So we've known for almost 3 decades now, this is the study from McMurray and Rader in 1985, that particles get lost to the walls in very predictable manners, and you can sort of account for that effect. Some clever experiments that have been done by the Boulder group have shown the importance of the loss of condensable vapors absorbed into the walls of the chamber. But this third process, which is the loss of condensable vapors onto particles on the wall, hasn't really been explored. And we try to do that using the Som-Thomas model. Okay, so we take Caltech data, thank you, John Seinfeld, for alpha-pinene SOA under low and high NOx conditions. And then we fit the model by accounting for all of the processes in our model: particle wall losses, vapor wall losses, as well as vapors lost to the particles on the wall. Then we perform forward model simulations where we turn some of these processes off. So when we turn the particle wall losses off, the orange curve, you get a slight increase in your SOA formation. But when you turn the vapors lost on the particle wall losses off, you don't get a significant increase in your SOA production. And that's because it's a very slow process to take something that's inside a chamber to the wall and then deposit onto particles that occupy such a low surface area on the chamber walls. So we've done this for 6 other precursors, including benzene, toluene, naphthalene, and so on. And we've produced parameters that can be used in a chemical transport model. And so the way we do that is we run the Som-Thomas model as a pseudo-atmospheric model, and then fit that pseudo data to develop VBS parameters. We compare those VBS parameters to existing parameters in a global chemical transport model like GeoSchem. We see that the SOA mass yields are significantly enhanced when we account for both particle wall losses as well as vapor wall losses. And we can do this for high and low NOx and across a set of precursors. And then we can run the GeoSchem model with these updated parameters. And we see that the organic aerosol concentration increases, particularly the largest in source regions. And we see slight improvements in the ability of the model to predict PM 2.5 mass concentrations that were derived from a combination of CTM and satellite data. Okay, so with that, I am running out of time, so I'll keep my key findings here on the screen. Thank you for your attention, and I can answer any questions.
That's a really nice holistic approach to combine different chamber studies. And, you know, I'm a global modeler, so is there hope that we will get some values to use in a global model that we will actually have to stop worrying about everything you just said because it's a solved problem eventually?
I mean, the optimistic answer is hopefully yes, right? But there's perhaps other relevant processes. I mean, we've only looked at some of the most dominant mechanisms for SOA formation and evolution and its influence on properties. There are many other processes that we have sort of ignored. For example, the model does not currently account for photolysis from visible light or UVA light, which is commonly used in chamber experiments. We typically still rely on dry chamber experiments. And so we don't have to worry about aqueous chemistry, but that doesn't mean that's not relevant for the atmosphere. I think there's hope, but I think the bigger point I want to make is that I think process level kinetic modeling is sort of the tool we need to use to try and study these processes and then develop parameters for global models.
Your point on the time-dependent diffusion coefficient I thought was really interesting. How is this really done? Can you expand on this a bit? Is that a composition dependence, or is it just like a fit function over time?
No, so I mean, both. So we're using I guess we can trace it back to Manabu's Nature Communications paper, where we use the molecular weight and the O to C, and I think the C star information as well, to calculate the glass transition temperature, and then we treat it as a mixture. It's a dry experiment, so we don't have to worry about water uptake. But then we use that to calculate the diffusion coefficient. Well, the viscosity first and then the diffusion coefficient, right?
Thanks.
I actually had a question. Maybe I missed this, but when you, for example, calculate the glass transition temperature, is this for a pure organic particle, or can there be some inorganic components in there as well? So the reason I'm asking is I'm immediately thinking, could we do this in PyPartMC, and how would we transfer this? And we rarely have pure organic particles. They're usually, ammonium sulfate or ammonium nitrate is also in there.
Right. So the experimental data set that we had access to did perform experiments with and without seed. The seed that we used was ammonium sulfate.
Okay.
But these were dry experiments, and so we assumed that the sulfate is organic simply coats the ammonium sulfate, and it is separated. Right. It's a core shell type of morphology. And so it really works for our model really works well for the experiments that were performed. But if those same experiments were performed at a higher relative humidity, we don't know.
Anyone doing that, or is that possible? Or
I mean, there's reasons why chamber experimentalists don't like to perform wet experiments, because they like to isolate the sort of vapor pressure pathways from aqueous chemistry. There is a increased interest to perform experiments that are more representative of atmosphere relevant conditions. And as more of those data sets become available, we can start to test our models and parameters against those revised data sets. But there aren't a lot of, unfortunately, high RH chamber experiments.
Okay, thank you. Let's thank our speaker again. Okay, moving on to our next speaker, that's Ryan Schmedding. Ryan is a senior grad student in Andy Zünd's group at McGill University, and his research is focused on the role of aerosol particle size in determining aerosol physicochemical properties.
Hi, good afternoon. Thanks for coming to my talk. I think this one will really complement some of the talks from this afternoon really well. So I'm going to be talking about the roles of interfacial energy and size-dependent morphologies of atmospheric aerosols. So hopefully this is not a new figure to you guys, but as we go down in size in aerosol particles, they get much more numerous. And so we can see that like the smallest particles, those with diameters below like 100 nanometers, generally tend to dominate size distributions. And importantly, if we think of the surface area to volume ratio of these particles in the coarse mode here, it's pretty negligible. Sort of the total ratio is quite small. But then as we go to below 100 nanometers, the surface area to volume ratio of these particles gets much, much larger. And so it becomes much more consequential overall to the properties of the particle. Recently, there's been some analysis on aerosol phase separation and the role that size can play with that. So this was from Miriam Friedman's group, and they looked at particles going down to below 100 nanometers and whether or not these particles can phase separate. So they'll see that above about 100 nanometers, pretty much all the particles end up liquid-liquid phase separated. And then as you get about like 75 to 80, we start seeing some that remain in a homogeneous mixing state. And then below about 60, they're pretty much all homogeneous at this point. So something is going on here where some of these particles with the same composition at larger sizes are splitting into two liquid phases, and at smaller sizes, they're staying in the same liquid phase. hopefully this figure on the left here is also not new to you. But when we talk about surface partitioning, that can also have an effect on aerosol cloud activation. Particles with small sizes can have organic species move to the surface. And this species moving to the surface can decrease the surface tension of the particle, as has been discussed today. But more importantly, particles that are really small, because they have constrained surface area to volume ratios, anything that is in the particle that moves to the surface is then depleted out of the bulk of the particle. So you have your particle, if you make an organic film, some of that material is now no longer in the center of the particle here. And it also needs to be at equilibrium with the center of the particle. So you can have things like organic species, which will preferentially move to the surface of a particle. But then if you have like an electrolyte species, that will actually move from the surface to the bulk. So it's kind of a two-way street where things are going to the surface of the particle and things are moving to the interior of the particle. And so the surface tension reduction will impact your Kelvin effect. And that gives you that kind of decrease in your critical supersaturation here. But moving ions or electrolytes into the center of the particle can also modify the water activity component of a Kohler equation. So there's kind of two effects here. And we think it's pretty important to capture both of these when we talk about cloud activation. When we model surfaces, sort of like a classical thermodynamic approach would be to use like a two-dimensional dividing plane between a condensed phase and a gas. This makes some math a lot easier when you talk about surface tension, because it's just a single term that you add to your Gibbs energy. But it can complicate things because molecules have real volumes, so we need to account for that somehow. So in our models, we've been using a 3D interfacial region, and that has a finite depth delta here. We think it's probably on the order of about a molecular monolayer, but it's an adjustable value, so this is a bit of a fitted parameter. And then stuff partitions from our condensed aqueous phase alpha here to our 3D interfacial region up here. So our group uses IMFAC, which is an activity coefficient model, and this is how we actually calculate our equilibrium morphologies. So the two key things on this slide are the two lines in bold here. But basically, if we want to calculate the chemical activity of a species in the surface, we take our mole fraction or molality concentration here and multiply it by the activity coefficient given by IMFAC. We added this parameter T here, which can be a secondary fitting parameter. Most of the time we just set it to 1, but there's been some studies that say that this can vary from like 0.5 to 2 approximately. So there is some adjustment on surface activity coefficients. We then use that to calculate the chemical potential in the surface phase here. And one key assumption that we make is that we assume that the partial molar area, which is this script A for each species, is equivalent to like the pure component partial molar area. So all that leads to this equation down here on the last line. This is what's called the Butler equation. And what it is it's relating the log scaled activities and the surface and the bulk along with this value here, which is a reference state surface tension value. And that gives a solution surface tension. So at equilibrium, all these solution surface tensions have to be equal to the same value. And that gives us our system of equations that we use to solve for our equilibrium configuration. This value here, the sigma I naught, that's a bit important. So we know what it is for some compounds. So for water, we know it's about 72. For some organic compounds, it's been measured. For other ones, it hasn't. If you'd like to know more about how we estimate that, I'm going to shamelessly plug my poster at the back of the poster hall where I talk about estimating this value for atmospherically relevant species. So looking at some comparisons to measurements, because these particles are so small, it's really difficult to measure their surface tension. So a lot of measurements are done for bulk systems. However, because we're talking about systems with highly constrained surface area to volume ratios, we want systems that are measured in like a contactless way. And so really one of the few people who's doing that is Brian Bizdek. And he's been taking measurements of various binary systems. So this one on the left here is a water ethanol binary system, and the one on the right is a water sodium chloride binary system. So the three different colored lines here are for different interfacial thicknesses. So the orangish brown line is for like a thicker interface, so 1 nanometer. The black line is for 0.3 nanometers, which is about the size of a single water molecule. And then the green line is for 0.1 nanometers, so like smaller than half the size of a single water molecule. We see that if we set the surface tension, or if we set the surface thickness here equivalent to a monolayer of water, basically, that it actually agrees with both the bulk and droplet measurements pretty well. And if we set it to a thicker value for the water ethanol system, we get like a less responsive surface tension curve, and a thinner value gives like an overly sensitive surface tension curve. Looking at electrolytes, because those raise surface tension as opposed to decreasing it, we see kind of a similar thing. So with a surface thickness of 0.3 nanometers, again, we get pretty good agreement with the optical tweezer measurements. If we set the surface tension to be thinner, we kind of get the opposite behavior as organics, where the curve is not very responsive to increasing electrolyte concentrations. And if we make it a thicker curve, then we get an overly sensitive curve in this case. The purple here is another bulk measurement, so it's also in pretty good agreement as well. There's a lot of different ways you can measure surface tension in bulk systems, so we included that as another data set. Thinking about how that could impact, that bulk surface partitioning can impact the cloud activation for atmospheric aerosols. These different colors correspond to sort of the maximum supersaturations you could find in different cloud types, and the different shapes correspond to different models for bulk surface partitioning. So the triangles are the Butler equation, which was the approach I just described. The squares are the organic film approach, where we partition all of the organics to the surface. So it's not actually necessarily thermodynamically rigorous. It's not a true equilibrium model, but it's a kind of a maximum surface tension depression. And then the IAMFAC equilibrium circle here is a like weighted average of their component surface tensions based on their volume fractions. So we see like for this water subric acid ammonium sulfate system here on the left, figure A, but if you do the weighted average, you get to overpredict your critical supersaturations. And then if you use the Butler equation or the organic film, they're in better agreement in general, but they lead to lower critical supersaturations. Now, the figure on the right is a little bit more complicated because now I've introduced a color to it too, so there's more going on. So the red figures here are for co-condensation being disabled. So now we're only allowing water to move back and forth out of this particle. This is water in an isoprene SOA particle. And the black is allowing all of the isoprene SOA species to partition back and forth between the gas phase. So it's like 21 isoprene SOA species. So we see for this that the inclusion of co-condensation leads to depressions in the critical supersaturation. And so if you do the IAMFAC equilibrium without co-condensation, you get like really high critical supersaturations. And if you do co-condensation enabled with the Butler equation, you end up with pretty much the lowest critical supersaturation. So there's a feedback here on the internal composition of the particle and the gas particle partitioning. So we start to get this sort of nesting effect as things feed back to outer problems. Now, the concept of phase separation has been mentioned already today, so I'll briefly talk about that as well, because this is sort of the next thing that we're interested in. So we go from a single aqueous phase here on the left. Now we have phase separation happening. So we have our organic rich phase beta here in green, and our aqueous phase alpha here in blue. We still have our surface interfacial or 3D surface region here, but we also have a liquid-liquid interface between alpha and beta. So we use the same approach here, except with one key difference, which is that our reference state interfacial tension is 0, because we assume that it's the interfacial tension between two pure layers of compound I. So if you have like a monolayer of water and then a monolayer of water on top of that, the interfacial tension between them is 0. So we just set this value to be 0. And then we looked at some simplifications here just to kind of see like there's been other parameterizations for interfacial tension in the past, what that might look like. So we have this like negligible interfacial tension here that we just set it to 0. Then we use Antonov's rule, which is kind of this like older parameterization for surface tension, where it's the difference between, or sorry, for interfacial tension, where it's the difference between the aqueous phase surface tension and the organic phase surface tension. Then we looked at the Girafalco-Good equation, which is born out of Antonov's rule, and it's slightly more complex, but it relies on the geometric mean of the two phase surface tensions and this value phi here. And so phi can range also between like, there's a minimum value on it that's determined by the geometric mean of these two surface tensions. But if you set this to be too large, then you can start getting kind of negative surface tension values. So we just set this to be 1. Again, we're keeping things simple. And then I looked at 2 other parameterizations based on IAMFAC. So an activity coefficient where that T value for the liquid-liquid interface is 1/2, and one where that T value is 3/2. And then this last one down here, we said the activity coefficient for compounds in the liquid-liquid interface is the geometric mean of the activity coefficient for species I in the aqueous phase and in the organic phase here. So looking at what these different values give, or these different models give for interfacial tension. So I'll start with the ones that we know are basically incorrect. So IAMFAC 0.5 and IAMFAC 1.5 both give values that cross 0 at some point. So a negative interfacial tension is like not physical. So we said that these are not like valid methods of estimating interfacial tension because they give values that are negative. And then we see up here, this is Antonov's rule in orange, which gives really, really high interfacial tension values. So maybe this is like overestimating. Now in the brown and in the green, we have the Girafalco-Good equation in green and the geometric mean approach in brown. And these both give much more realistic values for interfacial tension in particles. So between the two of these, it's simpler to use the Girafalco-Good equation because it doesn't rely on an additional activity coefficient calculation, whereas the geometric mean includes another like sort of nested solver in here. So this is probably a good simplification for estimating interfacial tension. If measuring surface tension is difficult, measuring interfacial tension is even more difficult. So there's really not a lot of information on this for aerosol particles. There was one study from 2013 that looked at this, but they only gave 3 data points and didn't give uncertainty for what the interfacial tension value is. So this blue curve is for the Girafalco-Good equation. And then these are their 3 interfacial tension values, which we can see that this is still overestimating the interfacial tension in this water PEG particle. But so far, this is the best of the options that we have at the moment. So and it's simpler. So it's been good in that sense. But ideally, we would like these points to match up with this curve a little bit better. Now, sort of going back to the beginning, when we talk about size-limited phase separation, all these energetic contributions from surface tension and interfacial tension and bulk phase depletion can lead to some size-dependent phase separation, which is what we're finding here. So this is for a water PEG and ammonium sulfate particle, and we see that above like 150-ish nanometers, there's not really a huge effect on the separation relative humidity. And then as you go down, you see that the particle starts to phase separate at lower saturation ratios. We only ran this down to about like 20 nanometers in diameter. Below that, it starts to get really, really, really slow because the solver struggles a lot. But we can see that there's a pretty strong trend here where it decreases, but every particle we've tested still eventually phase separates. So we don't get this complete inhibition of liquid-liquid phase separation that some other studies have been showing. The colors here represent the log-scaled concentration ratios in the particle. So this is organic over aqueous phase, and we see at really small particles, there's a slight variation in the composition as well. So in conclusion, the estimated surface tensions that we get from our Butler equation-based approach with IAMFAC generally tend to match bulk measurements really well. including surface tension estimates and bulk surface partitioning, reduces critical supersaturations necessary for cloud droplet activation and Kohler curves. Using the Joe-Falco good equation or the geometric mean of activity coefficients gives the most reasonable values for interfacial tension and aerosol particles. And then IAMFAC predicted relative humidity of phase separation decreases with decreasing particle size.
I'm curious about midway through where you talked about that fitting parameter when you were estimating the activity coefficients in the interfacial layer.
Yeah, the t-value.
Exactly. So I'm kind of assuming that has to do with you're predicting activity coefficients for bulk, but using them in a, but can you talk a little bit more about that? Like why that the values, I don't know.
Yeah, so if you make the t-value like less than 1, then you would be saying that the surface is mixing more ideally. And if you make it greater than 1, then you'd be causing your activity coefficients to get larger, so they're mixing less ideally. In the supplement for our paper, we look at like sort of parameterizing things just based on T. And so for a lot of systems, it's very close to 1. And then there's a handful of systems that it like you have to set your T value to be like 20, which would just imply that the activity coefficient calculation for the surface needs to be adjusted essentially greatly because it's just not mixing very ideally in the surface phase. I think if a compound is like very surface active, but it also readily mixes in the bulk, then that might cause issues where like if we're trying to replicate a surface tension curve or a Kohler curve for something like malonic acid, which is like very, very water soluble, then the activity coefficient in that surface phase needs to be larger to account for the fact that it like is actually more surface active and that it's just like being kind of pulled into the bulk phase because it has a pretty high O to C ratio. So it's like it would not partition to the surface maybe as much as it should be to be in agreement with experimental data.
Maybe a quick one. You showed this 3D surface interface between the gas and the liquid, but between the two liquids, it's a 2D interface you have in the model. Have you considered if there a 3D interface would also make a difference?
Yeah, that's something I looked at as well. So you definitely could treat it as a 3D interface. Then the question becomes, so something I didn't cover is that we actually solve bulk surface partitioning as the outer problem. So we do phase separation inside bulk surface partitioning. So we solve the surface composition and then phase separation. So then the issue becomes like, well, where does the material for the liquid-liquid interface come from? Does it come from both alpha and beta? And then do you have two liquid-liquid interfaces? Like two layers that then combine to make a single layer, or like is it only coming from alpha or is it only coming from beta? So like sort of in the interest of speed and robustness, we set it to be a 2D interface, and then you can make like virtual activities in the surface where it's just like what would the mole fraction need to be there to solve the Butler equation. But we have looked at making it be a finite depth interface as well. But then it's also like, is it the same depth as the surface, or do we need to set it to be a different value? And it kind of introduces more uncertainty. So,
great, thanks. And let's move on to our next speaker. We're going to have Zach D'Aquino, who is a master student in the group of Professor Nicole Riemer at the University of Illinois, Urbana-Champaign, and he's going to speak about a highly anticipated topic we have heard about earlier, the Python version of PyPartMC. So the stage is yours.
Yeah, so I'm going to talk about some of the development work that we've been doing on PyPartMC, a Pythonic interface to a particle-resolved Monte Carlo aerosol simulation framework. And I wanted to start out with this figure here because it very nicely depicts what aerosol particles look like in the real atmosphere, and then some of the options that we have to represent these complex particles within our models. And so I'm sure everyone here is familiar with the bulk modal and sectional models, but I wanted to specifically highlight this particle resolved representation where particles are represented by discrete computational particles, since PyPartMC is an interface to a particle resolved model. So PartMC is a stochastic particle resolved aerosol model implemented in Fortran that represents the aerosol particles as discrete computational particles, and then models the microphysical processes that these particles undergo during their lifetimes in the atmosphere. So we can imagine that we have this person here on the left side of the screen who's teacher, researcher, someone interested in the wonderful world of particle result modeling represented by the right side of this slide. However, there are some non-trivial things that need to be overcome in order to get started with particle result modeling in PartMC. So the need to individually compile and install PartMC along with all of its dependencies, and almost unavoidably wrestling with incompatible compilers and libraries can be a bit of a mess for someone with less experience in computation. These advanced tools like CMake and NetCDF can be quite a challenge for someone who's just starting out. So I want to show how we're using PyPartMC to sort of dismantle that barrier to entry. So PyPartMC itself is written in C++, Fortran, and C. And then we use PyBind 11 to build the Python API from PyPartMC's C++ bindings. Continuous integration is handled through GitHub Actions. We use PyTest for test automation. CMake provides 3-language build automation. And due to Python's interoperability with other programming languages, PyPartMC is usable from Julia and more recently MATLAB. And we also have API, auto-generated API documentation on the web provided through PDoc on each pull request merge that looks something like this. And so putting all of these tools together and publishing on PyPy, we get a single command to install PyPartMC. And this grants the user access to the unmodified and versioned Fortran internals of the PartMC codebase on macOS, Linux, and Windows without any need for prior installation of PartMC or any dependencies. So now I'll get into some of the more technical details behind the development process here by going through a little example of what a typical development workflow would look like. So on the left-hand side of the screen, we have this box that represents PartMC, and within that box, we have this single Fortran file that contains the definition of a derived type that represents a single computational particle in a PartMC simulation. And then within this file, there would be all the associated subroutines and functions that go along with this derived type. In this particular example, I'm just showing a single function that computes total volume of a particle. And now I'll kind of show how we go through and grant access to this function in Python through PyPartMC. So now we travel to the right-hand side of the screen where we have this similarly colored Fortran file in this red color. And so we define this Fortran wrapper where its primary job is to call the native PartMC function. And then once we have this Fortran wrapper, then we need to move on and get this C++ wrapper, which is shown right next to it. And then the job of this C++ wrapper is now to call our Fortran wrapper that we just defined. And the reason this all works is because of Fortran's interoperability with C. So we bind through C in both Fortran and C++. And then we can have a C++ wrapper that calls a Fortran wrapper that calls our native PartMC function. Now, once we have our C++ wrapper, we have to pass this information onto PyBind 11, which then automates the API generation. And once the API is generated, we need to test to make sure that our wrappers work as we would expect. So there's this example test file in black on the right-hand side, where it's just a simple Python test program where we're checking to make sure that if we set the particle volume to some value, that this function will return that same value. So our wrappers are working as we would expect. So main takeaways from this slide is that PyPartMC operates with unmodified Fortran or unmodified PartMC Fortran code. So all the computation is still taking place in Fortran, and this makes updating versions of PyPartMC straightforward without having to modify a whole bunch of code in PyPartMC. Data remains in the underlying PartMC Fortran types. We're not transferring this data around back and forth. And the whole reason that this specific wrapping structure works in our project is due to the modularity of PartMC. So PartMC has many different modules where we have defined derived types and their associated subroutines, all kind of contained. And that's why we can generate these wrappings in a very straightforward manner. And then the main development feat on the PyPartMC side is that we have the C++ wrappers, which allow us to take advantage of the PyBind 11 framework that automates the API generation. So now I'll show some examples of some cool things that we can do with PyPartMC. So in this specific example, on the left-hand side, we have a user-defined function that uses the PyMeScat external package, not our package, just another Python package, to compute some optical properties of particles. And then on the right-hand side, we have this time-stepping loop from a PyPartMC simulation. And I want to note that in this example, time-stepping control is with Python. So we're able to call this user-defined function at every time step in our simulation to compute optical properties. So we can follow this star here on the screen and see where this function is actually being called in the time-stepping loop. And then we can use matplotlib or any other visualization library that we'd like to see some cool results based on this simulation. So this kind of shows this flexibility in external coupling that allows us to take advantage of libraries that already exist to generate some interesting results. And this also has implications in machine learning, since there are a lot of Python packages that are used for machine learning. And it would not be so straightforward to do this if we were just operating with the Fortran PartMC code. So now in this next example, I'm showing a snapshot, just a small piece of an entire simulation that runs in the cloud through Google Colab. And one thing that I want to note here is that time-stepping control remains with Fortran. So there's some flexibility in the way that we've decided to develop PyPartMC so that the user can decide whether they want time-stepping control to be in Python or remain with Fortran. And since we have time-stepping control in Fortran, we can see on the left-hand side of the screen that we still generate these netcdf files for every outputted time step. This data is generated through the simulation in this notebook. It's outputted, and then it's also processed in the exact same notebook. And then we can similarly use matplotlib to visualize or whatever the user would like. So the whole point of this is that we're kind of bringing together all of the best tools to benefit users of PartMC. So we use Fortran for computation, and we use Python for the user interfacing, and we kind of get the best of both worlds. So most important things from this slide is that the entire simulation is running in Google Colab. We have this choice in time-stepping control, and data generation and processing all happens in a single notebook. And you can imagine that this could be particularly helpful in teaching applications, peer review, since dissemination is very simple. Just send a notebook around. And so now I would just like to say that all of our development is open, and PartMC is open source. However, the point of this is that open source is not necessarily good enough. We need to kind of dismantle these barriers to entry so that anyone who's interested has more of a fair shot of getting involved. And I'd invite you to check out our GitHub page and also our documentation. And if there's any suggestions or questions that aren't addressed here, then please use the issues tab on GitHub. Thanks.
I'm not a Python user, so forgive me for the probably simple question. You mentioned about wrappers of wrappers that are calling Fortran and C++. How that does not affect performance, and how do you avoid having a compiler to compile the Fortran to be called?
Yeah, so you're referring to this where we have wrappers calling
Yes.
wrappers? Okay, yeah, so the reason that we don't have any, we don't really have any degradation in the performance, because all of the underlying computation is happening in underlying original PartMC Fortran code. And the reason that we have this wrapping structure is to preserve that computational benefit. And we can't go straight from Fortran to Python. So we have to go through C++, and then we have to force a common ABI through C, which is why we've done this. But essentially, Python is not handling any of the computation. So we're not getting any loss there.
You still have to compile the Fortran code, though.
Yeah, it's pretty
So
good.
that is still part of the wall that you showed early on.
Sorry, I didn't hear you.
It is still part of the wall that you showed early on, right? That the compilers is something that blocks the user from having an interface that is simple to use.
Yeah.
Like your slide 2 or something.
Yeah, but the compiling is the stuff that we handle in the back end so that the user doesn't have to.
So this is really, really cool. Nice work. And I think this is really exciting. What would it take to make this PyPartMC mosaic?
That's a great question.
Like what could you, perhaps what could you use from, do you need something from, say, anyone at the PNNL community who maybe develops mosaic? Is that like what needs to happen for that?
Yes,
Broad-
so
Yeah.
if you have,
Sorry, this is a really unfair question. As Jeff just pointed out.
okay, if you have mosaic, then you can in a fairly straightforward way, couple PyPartMC with mosaic. But the reason why we haven't done this is because mosaic isn't open source. So we're kind of leaving that up to other people to decide.
Thanks. This is really interesting. And I appreciate that you're preserving the computational efficiency by keeping PartMC in Fortran. I was just curious, could you characterize the development cost of writing the wrappers in contrast with actually coding PartMC in Python? Should you not have cared about preserving the computational efficiency of that part of the code?
I don't even think that was something that was considered, just because the computational cost would be so different. Since PartMC is a particle resolved model, it's kind of inherently costly. So to do this in Python does not make total sense. And this wrapping structure is fairly straightforward. I know it might seem kind of convoluted based on how many different files that we have here, but it is straightforward. It doesn't take too much time due to the modularity of PartMC itself.
Then we're moving to the last speaker in this session. The last speaker will be Dr. Adam Milsom. He's a research fellow at the University of Birmingham, where he works with Professor Christian Frank. His talk will be about another Python package, which is MultilayerPy. So please welcome Adam to the stage.
Thank you very much, and thanks for inviting me to sunny California. Yeah, so I'm Adam Milsom. I'm a postdoc at the University of Birmingham in the UK. And yeah, so another Python package. So this is called MultilayerPy. It's a Python package for creating and optimizing these multi-layer models of aerosol and film processes. So first of all, I'll thank the people involved in this. So a lot of this was done during my PhD. So Christian Frank is still my current PI. So he's at Birmingham, and Adam Squires was my co-supervisor at Barth. And then Amy Lees, who was a master's student with us She really helped with the development and telling me what was wrong. So that was very helpful. And I thought I'd put some pictures of some supervisors actually doing some work. So on the bottom right there, there's my two supervisors trying not to break what I made. Okay, so this is, so this is a really pointless slide because we're all here for the same reason. So aerosols are important. But I thought I'd just hammer home the point that it's important to understand what's going on with them because they have this climatic impact. You have this, this formation of clouds, which interacts with the sun's radiation, this direct interaction as well. But there's also this interaction, this air quality aspect. If you breathe in particles and they have something that's not so good for you to breathe in, then that's not so good for your health. And so it's important to understand them. That's the point of that slide. But kinetic multi-layer models are the name of the game here. So the concept is you have an aerosol particle, so it's a particle resolved model, and you split it into a number of bulk layers. You can do that for a particle or a film, and the actual model resolves mass transport between each bulk layer. So that middle schematic there shows you that you can resolve bulk diffusion as well as the movement of things from the gas phase to your particle surface. And then you also resolve reactions at the surface and within the bulk layers as well. It's quite detailed modeling. There's a lot of input parameters. And there are two main models that I focus on and that MultilayerPy focuses on. So it's the kinetic multi-layer model of aerosol surface and bulk chemistry. So KM sub and then KM gap, which is basically the same thing, but you account for the expansion and contraction of these these bulk layers. And so you can look at condensation and evaporation and that kind of thing. And that was developed 10 to 15 years ago now by people in this room. And I've sort of carried this on as well. So, okay, so why are these models useful? So I'm going to take you through my PhD in like 3 slides. So I was interested in surfactant aerosols, and in particular, what do they do if they start organizing themselves? So my whole question was, what is the effect of molecular self-organization on aerosol processes? So my favorite molecule is oleic acid. So if I can, so there it is. It's a surfactant. It's emitted in cooking emissions as well as in the sea spray aerosol. And there's this observation that oleic acid seems to last longer in the atmosphere than is predicted in the lab. And so why would that be? There must be some sort of physical process happening to cause that. And the proposition is that under certain conditions, oleic acid can make one of these self-organized phases. And these are interesting because they're quite gloopy. So oleic acid is basically olive oil. When you make one of these phases, you get toothpaste consistency type mixtures. And so my whole thing was looking at how does that impact on chemical reactivity? So this sort of simulated atmospheric aging of oleic acid. The take-home message is that it slows things down. So when you get a viscous, gloopy system, you slow everything down. And so that has implications for potentially the climate, because if you've got a surfactant lasting longer in the atmosphere, then it's more likely to have an impact on cloud droplet growth and formation, as well as this health impact. If you've got a gloopy organic phase protecting nasty things in your particle, you're more likely to breathe it in and have bad things happen. So there's a number of studies from that. And just to zoom into the modeling side and why the kinetic multi-layer modeling was useful. So I have many hats, experimental and modeling, but so I developed a way of measuring reaction kinetics using X-rays and then complementing it with Raman spectroscopy. And we looked at films of this oleic acid proxy. So this is the sort of a bilayer form of it, which is quite gloopy. And we did some reactions, got some kinetic data, and then I applied one of these multi-layer models to the data and optimized it. So these models have lots of input parameters, and the stuff I didn't know about this particular system was things to do with viscosity and diffusion. So I varied those parameters in the model to get an optimized model. And then from that optimized model, I could go to, I could run the model under more atmospherically relevant conditions. So ozone concentrations in this case, this is all ozonolysis reactions, as well as film thicknesses. So the take-home message is when you go from this disordered liquid form of oleic acid to the ordered form, for about a 1 micrometer film and about 30 ppb of ozone, you get about a 10-day increase in the reactive half-life of oleic acid, which is like huge. So I'm not suggesting there are particles of pure self-organized oleic acid floating around, but it could go some way to explaining why oleic acid seems to last longer in the atmosphere. And then the other sort of selling point of these models is that they're depth resolved, so you can get this concentration or diffusion gradients visualized with this sort of model. So again, this is the same model I optimized, but now I've got a depth resolved picture of the system, time on the x-axis, and this is the surface of the film. This is where we deposit on the substrate, and we've got ozone attacking the film over time. And here, the heat in this heat map is the diffusion coefficient of ozone throughout the particle. And in this model, we built in this crust forming as a late stage reaction product, which slows down and limits the reaction rate, and that made the model fit pretty well to the data. And later on, we experimentally confirmed that there was actually a crust forming. So another hat I wear is I do single particle levitation experiments where we used X-rays to see this crust forming on the outside, which is quite cool. But that's the power of this sort of modeling. Okay, and we paid a lot of money for this cover image. I'm going to make you look at it for a few seconds, but it's basically everything is summarized in this study we just published. So please go and have a look at that, and a couple more seconds, and that's the money's worth. Okay, so yeah, so why did I make a tool to make these models? So I had a few frustrations when I did this modeling initially, because I essentially reinvented the wheel. So this modeling's been around for a while, but there's nothing really to go on. So they're complicated because you've got lots of input parameters. You've got stuff to do with diffusion, reaction rate coefficients, sticking coefficients, if you've got something that likes to stick to a surface or not. That's a lot of things to put in there. So it's very complicated. There's a lot of things to type out if you're doing it manually. So it's time consuming. If you're just one person doing it, then it's error prone. You're going to make mistakes. And so it's not always easy to modify the model either. If you're halfway through making the model, you've got an idea of changing something. If you're going to start copying, pasting code randomly around your file, you might run into problems as well. And so does that make it reproducible? So most studies don't share their code, so you can reproduce what people do, but it's kind of hard to build on what someone else has done. So that's where MultilayerPy comes in. So we've gone back to this concept. So on the left-hand side, we've got our idea for a multi-layer model for a particle or film. And I want to get to the right-hand side, right? I need to get to this model side, but I don't know how to do that. So let's use MultilayerPy, which is the toolbox to do that. Okay, so if you've been asleep the whole time, this is basically the take-home message is MultilayerPy will do this for you. And here's the cell for it. So it's modular. So this left-hand picture, every box here is essentially like a Python class. So it's an object-oriented way of doing things. So you can chop and change these building blocks for your model. So you define the model type, so KM sub or KM gap, the reaction scheme. So what is reacting with what in your model? Or do you even have a reaction? So you can do stuff with water droplets, for example, and have no reactions. Diffusion regime, that means, do you have composition-dependent diffusion in your particle, which sometimes is useful, especially for what I was doing with these viscous systems. And then you obviously define what's actually in your model. What chemicals do you have in your model? And you mix those all together into this model builder object, which produces the model code. And yeah, so that model code is written in a way that it's readable. So it's automatically commented. You can kind of find where you are in the code. And you can edit it yourself. So if you've got some idea for some funky process I haven't thought of, then you can edit that code and then run it in MultilayerPy and see what happens. And yeah, so then you can run the model. You get the standard output, which you can then use to plot in your own way or do some sort of analysis further down the line. And then if you have some experimental data, you can optimize that model to the data. So there are a couple of algorithms. There's a local optimization algorithm, as well as a global one. And there's also a statistical way of determining parameter uncertainty. So this MCMC sampling, which has been mentioned today, which I'll go into a little bit more in a few minutes. Ooh, press the wrong button. Okay, so yeah, so I've said it's modular. It's reproducible because it's all readable. It's under an open source license, so it's only ever going to be open source. So the idea is that people take this and run with it and share it with their publications, and it's scalable. So you can quite easily just install this onto your multi-core systems, like a high-performance computing system, and and carry on and do some bulky calculations. It also has its own YouTube channel, so if you want to hear me talk more about it and actually learn how to use it. So one of the big barriers for people using new software is that people, if you're not a coder, it's a bit scary telling someone to write this model with this package. So I've made some tutorial videos for people to start using this for themselves. Okay, so so here's like a use case of this package. This was a recent study I was involved with. So this was led by Martin King at Royal Holloway University in the UK, and it was a very large team. So some people went out to Antarctica and sniffed the air over there and collected some aerosols. The funny thing was the original draft of this picture had a polar bear on it, which they don't exist down there, so that's to redraw it. But so they went to so they went to Antarctica, sniffed the aerosols there. They went to an urban environment, got some urban aerosol samples, and then some wood smoke burning, which is quite topical at the moment. And we took those aerosol samples and we coated them onto an aqueous surface and did this neutron-based technique where you can look at reaction kinetics, in this case with OH radicals, which you find in the atmosphere. And yeah, so I did the modeling for that. So I got their kinetic data and did some modeling of it using MultilayerPy. And just to highlight, this got an award from this neutron source societal impact award for some reason. But yeah, it was it was a nice award to get. Okay, so here we go. So my MultilayerPy, I use that to fit to some of these data. So this is like a sample of what we fitted. This is kinetic data for these. This is for the remote Antarctic sample. And what you can see, I fit two models to the data. So you've got this dashed line where it's a model where I don't have a residue at this air-water interface we're looking at. It fits reasonably well at the decaying portion of the curve, but it doesn't fit well at the end. And that's the same for this plot. But then I fit a model which did have sort of a residue on the air-water interface, and that fit very well to the data. That's the black line here. And I mentioned MCMC sampling. If you've got uncertainty in the data points you're fitting to, there should really be an uncertainty in the model you're fitting to it. So MCMC sampling essentially just, if you initiate a load of parameter sets, a load of models in your parameter space, you let them wiggle around the parameter space, and the algorithm is such that they converge around the average sort of best fit parameter. And from that, you can get a histogram and then a plus or minus value for your fitted model parameter. So it's not a fitting algorithm, but it's a really good, really useful algorithm for determining an uncertainty in your model. So from those optimized data sets, from those models, you can then run the model under more atmospherically relevant conditions, in this case, OH radical concentrations, which you might find in the atmosphere, especially between 10 to the 6, 10 to the 7. So for each of these types of aerosol, you're looking at about a reactive half-life for the reactive portion of the film of between about 10 minutes to an hour or so. But if you go to lower OH concentrations, you could go up to days and maybe even a week. So that's the kind of power. So we've gone from the idea of a model to making the model and then applying it to some real world stuff to then have a sort of real world implication in relatively few lines of code. So I didn't show you any of the code here. But if you're interested, you can go onto the YouTube channel and have a look. So yeah, so just in the last minute or two, so I really would like to encourage people to use this. So currently it's just a one-man team. It's just me doing it, so it's kind of hard for me to keep up with people's suggestions. But I really would like people to start going onto the GitHub page and finding where I've made mistakes or where might things be more efficient. What do you want out of this sort of package? Because there's potential there for it to be applied to a lot of things. And I'm very happy because there's some people actually in California who actually use the package without me telling them to, which is kind of the idea. So I'm very happy. And also they used oleic acid, which is my favorite molecule. So I was very happy when this came out in the summer. So yeah, I mentioned the YouTube channel. So please search MultilayerPy, where I've got some tutorials. And I did a webinar, a live webinar last month, but it's still on the YouTube channel, so you can go and have a look at that. It's got the GitHub page, which is again, search MultilayerPy, you'll find it. And any specific questions to do with MultilayerPy, if you use that address, then I can address things separately there. But obviously you can contact me through other means as well. So yeah, I'm kind of well within the time there, so I'll stop there. So thanks for listening, and I'll take some questions.
Hi, I noticed that you indicated this could be useful for layers as well, and that I'm curious if it's coded in a length scale independent way where it could be used for surfaces on which reactions are happening, say for indoor air quality. And is someone doing that yet?
So wait, so you're asking about what scales can you do with this sort of model? Yeah, so you can go as thin or as thick as you want. So I've modeled things that are a few nanometers thick and a few micrometers thick. And you can do spherical and planar geometries as well. So there's scope there to model whatever you want. I mean, the thicker your film or particle, and if you want to keep a very high resolution, the more bulky the calculation is. So you just need to consider that kind of thing. But I mean, anything's possible. Yeah.
Really nice work. Is it pretty trivial to add sort of gas phase chemistry as simply a module to your MCMC?
To the model, yeah, you can couple anything. So so in the diagram that describes it, I won't go all the way back to this beginning, but you've got this gas phase, right? So in theory, you could just put in a box model there and have some gas phase chemistry that's happening, and then you'd have, and then whatever from the gas phase would stick to maybe your particle and that kind of thing, and do that sort of thing. There are some variations on the KM submodel that sort of do that. So there are different compartments. So that's kind of what other people have been doing, but yeah, it's definitely possible to do that kind of thing.
Yeah, thank you. And one more question. So can you talk a little bit about the computational cost associated with doing simulations and maybe place that in some sort of benchmark case?
Sure. So I don't have an actual benchmark to go by, but if you want to model, so most model runs, if you've got a well-mixed system, say 100 model layers and you've got a 200 nanometer particle, it would take a few seconds to run for one particle. So in theory, and if you've got a very powerful computer, it gets better. But yeah, it's written in Python, but a lot of the functions I use in there is stuff that wraps C code. So it should be fast enough. It's not in pure Python, no. So I think future things would involve there are now wrappers for like C and Fortran type code that you can use in Python. I think previously the person before me was talking about that kind of thing. So there's potential to improve the speed of these models.
Hello, nice talk. I'm pretty interested in the previous the KM model, the multi-layer model.
Yep.
So that model it assumes a spherical structure with multiple layers. So inside the model, how can you make sure there's certain amount of some maybe inorganics that just exactly take up the whole layers, and there's other maybe organics just like one layer above that layer.
The phase separation. So yeah, I haven't done that myself, but it's very possible. So people in this room, I think, have actually done this sort of thing where they've modeled like a core of stuff, and then they've got like a shell of stuff as well. So you can initiate the model like that. Another interesting concept would be can you account for surface active things? Can you put that thermodynamic pulling power towards the surface, and then start modeling surfactants partitioning to the bulk and to the surface and that kind of thing. But that's like an idea for the future. But it's possible, yeah.
I thank you for the lively discussion. Let's thank Adam and all speakers of the session again. So I think this concludes the session, and we have now a medium-sized break, and we reconvene at 3:50 here for the last keynote speech. Thank you, everyone.